Yeah, thank you very much. It's very exciting for me to be here. So I thank the organizers for giving me the opportunity to present our work. I'll be talking about positive and negative signs in the renormalization of effective field theories and the relation to positivity bounds. That's based on this work that recently appeared on arXiv together with Yopang and Jasper, who are both here. So please talk to them. So let me first set the stage by introducing effective field theory, which is the framework that I'll be working in during this talk. So the idea of effective field theory is to provide a model-independent description of high-energy physics, and in particular, one in which the high-energy degrees of freedom, which might live at some high-energy scale called lambda UV here, they are traded by a sum over local interactions among the low-energy degrees of freedom. And these local interactions are parameterized by three parameters CI. What I'll be talking about holds in generic effective field theories, but I'll be mostly taking context and motivation from the standard model of effective field theory. And in the standard model of effective field theory, there is a very large parameter space, which might be quite overwhelming to work with. Already at lowest orders in this effective field theory expansion, you reach up to tens of thousands, well, more than 10,000 if you go to order 1 over lambda to the 4, free parameters. And so the idea would be to discover new physics, unknown physics at high energies through measuring non-zero values of those parameters, but confronted with such a large parameter space that is difficult. It is made even more difficult because these parameters, they mix under the renormalization group equations. So you cannot study them single ones in isolation, because then at lower energies, they will turn on other parameters. So this really requires us to get a good handle on this parameter space to understand the theory well, and to identify some universal structures in generic effective field theories. One such universal structure is given by positivity bounds on these parameters, which reduce the freedom in the parameter space. So the main feature that positivity bounds rely on is the fact that effective field theories provide a predictive framework at low energies, but they have to be UV completed at some high energy. And then using very basic assumptions and very rigid assumptions on the UV physics, namely unitarity, locality, analyticity, and Lorentz invariance, you can constrain the parameter space of your effective field theory by the fact that the effective field theory has to be UV completed. So in the rest of my talk, I will not actually be using these type of methods. So I'll allow myself to quickly review them just for the context. So the idea is to consider your amplitude as a function of S in the complex S plane, and consider different contour integrals, where using Gauch's theorem, you can relate the contour integral for small values of S that's within the regime of validity of your effective field theory to contour integrals at large S, which then is in the regime of your full UV physics. And a simplification that can be made to simplify the complex structure of the amplitudes is to approximate your effective field theory at tree level. In this case, in a massless case, in this example, you just have a pole at the origin, and so this contour integral just picks up the residue at the pole, and this is something that you can calculate, and therefore it becomes can be written in terms of your Wilson coefficients. So in equations, that's what I just said. That here also, by the way, I'm dividing out by some power of S. So this contour integral picks out the residue at S equals 0, and this corresponds to specific Wilson coefficients. On the UV side, we don't know what the UV physics is, so we don't know how to calculate it, but some basic statements can be made. For example, the integrals around the branch cuts, they give the imaginary part, which will be positive due to unitarity. And then the behavior at S into infinity, there are some basic results which bound the behavior of the amplitude at large S, which allow you to set this to 0, which is called the Froissart bound. And so that using unitarity, that results in the fact that even though we don't know how to calculate this, we know that it has to be positive due to the optical theorem. Going back all the way to our starting point from the effective field theory, this relates to a statement that some Wilson coefficients in your effective field theory have to be positive. Okay, so in the standard model effective field theory, this has been studied quite well, but the effects on how effects of positivity on the parameter space are. For example, there's this in the sector of 4 Higgs operators with 4 derivatives. This turns into a basic statement about the parameters. So here's operator 1, 2, and 3, given parameters C1, C2, and C3. And they have to satisfy these bounds here, derived at tree level. So what conceptually one would like to do is, when confronted with experimental studies that try to measure such parameters. So here's a CMS result that constrains the parameter space of C2 and C3, where this plot should be interpreted as if the actual values, meaning the values in nature of these couplings, will be outside this region, then we would have seen those effects in experiments. So since we haven't seen those effects, that means that the values of these couplings are expected with some level of confidence to lie within this region. So now the idea would be to supplement this experimental analysis, with our information of positivity bounds. And in this way, using the fact that C2 has to be positive, you can separate this parameter space into 2 regions. One is allowed by positivity and one would be forbidden. And this thereby reduces the parameter space. In doing so, one should be careful. For example, one should ask the questions, how should we interpret things if we find new physics actually in the forbidden region? And in particular, one should be careful because I've derived these bounds, or the derivation of these bounds have assumed that we work at tree level in our effective field theory. So in particular, one should be asking the question, what happens if we include loop corrections in our effective field theory? How sharp should this boundary be between allowed and forbidden region? Also, given the fact that these parameters, they depend on the renormalization scale. Okay, so these questions have been asked also in the literature, which I just briefly wanted to review as well, where the main statement is that once you include loop corrections in your effective field theory, your dispersion relations do not place bounds on individual Wilson coefficients anymore. Instead, they place bounds on, in general, all EFT parameters, and therefore the statements become way more complicated. You cannot just say that single parameters are expected to be positive. And in fact, this allows for these parameters to become negative. For example, in the standard model effective field theory, for those parameters that I just showed in the previous slides in that experimental analysis, if you just consider simple UV completions, you find that both with the matching calculation, so matching to those UV completions, you find negative couplings, but also the renormalization, even starting with positive couplings, doing your renormalization in the effective field theory will result in negative couplings as well. So here, okay, let me also mention that in certain cases, when you can argue away the effects of those branch cuts in the effective field theory, you can derive non-trivial constraints on the renormalization group equations. So here I want to distinguish these 2 types of calculations. The matching step is really, by definition, a step that is in relation to the UV theory, because we're matching the UV in the effective field theory. While the renormalization is something that you can compute within the effective field theory. So in principle, that should not know about your UV assumptions or UV physics. So for this reason, in this talk, what I want to do is shed light on this story, the loop corrections to the positivity bounds, from a purely effective field theory perspective. So purely within the effective field theory, I want to ask the question or try to understand the impact of renormalization on positivity bounds, where I will be using consistency of the effective field theory, namely unitarity, analyticity, and Lorentz invariance, but I will not be assuming anything about the UV. For example, the boundedness at large as of the UV amplitudes, I will not assume. And my derivation will hold for any spin, where if you want, you can interpret it as spin less or equal to 2. And yeah, so this plot I will return to later, but the type of questions are, given some value of the Wilson coefficients at the matching scale, do we expect them to increase or decrease, and can they become negative at lower energies due to renormalization? This is what we're going to work towards, just so you know what I'm doing in a short derivation in the next slides. I want to derive an equation for the beta function in the forward limit, which depends on quantities that are manifestly positive. Okay, so this has positivity in renormalization. Yeah, there's nothing to do. It's fine. Okay. Yeah. So let me start with the setup. So for simplicity, I will consider only bubble type diagrams where these vertices are local or contact interactions. I'll consider massless particles, and so in particular, these type of diagrams mean that I will not consider 3-point vertices, and I will not have to deal with infrared divergences. Also, because of this type of diagrams, there's only one momentum scale flowing through the loop, which is the sum of these two momentum going in. So in the spirit of this conference, I will compute the renormalization using amplitudes, where we rely on the basic fact that amplitudes do not depend on the renormalization scale, where I'll be using dimensional regularization. So from this fact, you can the scale dependence in your tree level amplitude is encoded in the scale dependence of the parameters. Those are the beta functions that we're after. And this is compensated by the explicit logarithms log mu in the one loop amplitude, such that the beta functions are related to those logarithms. Those logarithms come with the Mandelstam variables in the massless case, such that the beta functions can be accessed by the discontinuities across the branch cut of those logarithms for all the ST and U channels, where importantly, you have to consider all the 3 channels. Okay, so using unitarity, those discontinuities can be rewritten in terms of this phase-space integral over product of tree level amplitudes, where again, we have to be using considering these 3 channels. So this is this relation between the beta functions of the EFT parameters and these products of tree level amplitudes is a simplified case of a more general formula derived by Karen Ho and Matthias Wilhelm, who spoke earlier today. Where there's one difference here, which we're allowed to do because we're considering this simplified case, is that we're considering only amplitudes, and strictly speaking here, you consider form factors, which results in a subtlety that I'll mention in the next slides. Okay, so let me copy over this formula to the next slide and start using it. So I want to emphasize first that this formula is valid for generic on-shell kinematics, but it may be simplified if now we take the forward limit on both sides of this equation, assuming that this tree level amplitude will survive in the forward limit. So everything I derive will just hold for those parameters which contribute to the forward limit. So now studying those different channels separately. First, the S channel. In the forward limit, the incoming state and the outgoing state are the same. So this phase-space integral simplifies into something which becomes the square of the amplitudes. And using unitarity, this can be related to the cross-section and is sign definite, which relates us to the statement that this discontinuity contributing to the beta function is sign definite. So it's negative because of that minus sign in front. Where here, to derive this, I've assumed that S is positive. So given this sign, so in general, there will be an effective field theory expansion with different powers of S. One of the terms in this expansion will be some number times S to the n, where this number is negative. Okay, so similarly, this is the S channel. Similarly, for the U channel, again, the incoming and the outgoing states are the same. Now, however, here's the subtlety that to access this discontinuity, now we're taking U to be positive, which this sort of analytic continuation we're allowed to do because we're expecting just a monomial in U. So not expecting any subtleties changing this kinematic region. So this is the same as the S channel. Again, we find a definite sign in the contribution to the renormalization from the U channel. However, the T channel is different. So in the T channel, now we do not have that the incoming and the outgoing states are the same. So here we have to do slightly more work, which we will do by just doing simple dimensional analysis of the integrand here of the phase-space integral. So L1 and L2 are the loop momenta. And H1 and H2 are the helices of the internal particles, and N1 and N2 are the derivatives acting on the internal lines. And so by Lorentz invariance, since we only have a single scale flowing through this loop, by Lorentz invariance, it follows that the result of this phase space integral will be proportional to P1 minus P4 to some power, the power given by this exponent. So as long as the exponent is positive, this means that in the forward limit, where I'm taking the forward limit after doing the phase space integral, in the forward limit, this contribution from the T-channel will vanish. So the only case in which this exponent is 0 and in which we therefore cannot claim that this will vanish will be in 5-4 theory with 5-4 interactions. So in any other case, the T-channel diagram or T-channel discontinuity does not contribute in the forward limit to the renormalization. Okay, so bringing those 3 different channels together, what we have found is exactly what I set out to try to find, is that in the forward limit, the scale dependence of the Wilson coefficients encoded in this tree-level amplitude, they're given by the sum over the terms from the different channels where these coefficients are negative. In the forward limit, U is also minus S, so you get this relation where if N is an even number, you have control over the sign of the renormalization. So in terms of mass dimension, this translates to the fact that mass dimension 8, 12, 16, we have control over the sign of the running of the EFT parameters from these type of bubble contributions. So there's one comment which is a little bit, I think, technical to talk in sort of abstractly, but so let me try to exemplify this. I'll mention this again about the cross term in an example. So here I'm giving this example of the mixing into operators with 4 Higgs fields and 4 derivatives, given by double insertions of dimension 6 operators. So for example, these coefficients come from operators with 4 Higgs fields and 2 derivatives. So here there are contributions from scalar fields in the loop, gauge bosons in the loop, and fermions in the loop. And here the results are given in a generic basis, which is the conventional basis people use in the literature. I've defined these variables just to make the notation slightly cleaner. But the main thing that I want you to observe is that here the signs are not fixed. There are positive signs and negative signs, which comes from the fact that this is a generic basis. And our derivation before has assumed the forward limit. So once you start using this information and try to exhibit this universal structure, if you go to the basis in which the parameters contribute in the forward limit, so there's 3 different amplitudes, and in those forward amplitudes, and in those forward limits, these parameters contribute in these linear combinations. Then you see that the RG contributions are fixed sign and also simple. So what about the cross terms that I skipped over before? So I wanted to point out that here every total contribution is sign definite. However, the cross term, namely CH box times CHD, it isn't required to have a fixed sign. But the point is that you can always complete the square, and therefore you know that regardless of the values of CH box and CHD, so regardless of the UV completion, the contribution to the renormalization is with a fixed sign. Okay, so to conclude this, this type of contributions, they inform us that in the IR, so this minus sign means that going towards the UV, these parameters shrink, but towards the IR, these parameters will grow. So from these contributions in the IR, the parameters will become more important. However, here we have only considered one type of contributions, which is the contribution from dimension 6 squared. And as I said, these type of cross-term contributions between different parameters, they do not need to be sign definite. So we need to have another type of information or knowing when do these contributions dominate, so that we really know that the parameters will grow in the IR. And for this, you need to impose some sort of perturbativity argument about the size of the EFT parameters. So in what we call weakly coupled effective field theory, all the parameters are small as in the standard model. And in this case, we do not have a clear hierarchy between these two contributions. So in this case, you might indeed have that the parameters decrease towards the IR, and they might even become negative, as the literature has already pointed out. However, in a more strongly coupled effective field theory, in which we don't mean that the loop perturbation breaks down, because this is just the EFT parameters, there's still a high energy scale, which makes the parameters small. However, the dimensionless coefficient, once you consider those to be relatively large compared to the standard model values, then this term dominates and we have control over the sign of the running. And just to point out that this is not some something very unnatural. So this is the natural situation in chiral perturbation theory, and agrees with experiments, the experimental values of the coefficients in chiral perturbation theory. So in those cases in which the effective field theory, so in those type of effective field theories, we know that towards the IR, the parameters grow. Okay. So I wanted to mention a few applications and extensions of our work, which mostly try to probe future directions, but extensions which are not immediately implied by our work. So for example, as I said, our conclusions apply to mass dimension 8, 12, 16, etc., but not to mass dimension 6 directly. However, with a little bit of extra work, they also apply to mass dimension 6 to all contributions in the standard model effective field theory at mass dimension 6 from double insertions of dimension 5. And this is particularly strong because the usual positivity bounds do not apply at mass dimension 6. Also, I want to point out that we started exploring the results in the presence of three-point interactions, where this is a very simple case where we still have basically a bubble diagram, and therefore our calculation just works. And so this includes, for the running of the 4 Higgs operators, I included those contributions from F cubed, which include all standard model effective field theory contributions from dimension 6 squared into these operators, and for all of them it's sign definite. But there remain further questions to ask about topologies with 3-point vertices in more generality, and that's for future work. Also, as a simple extension of our work, what we basically derived is that in the forward limit, the T-channel diagrams do not contribute to the renormalization. So in those cases in which the T-channel is the only diagram available, that immediately implies a non-renormalization result that you do not have the RG mixing, predicting zeros in the mixing matrix. Okay, and yeah, this is a simple example in gravity, which just works exactly because we have only this type of bubble diagram. But if you include the minimal coupling to gravitons, you will get 3-point vertices to which will require further work to say something about them. Okay, so let me end this talk with a conclusion, trying to summarize what I've been saying with this figure. So on this figure, if you schematically try to interpret the x-axis as somehow the parameter space, the value of the parameters, and the y-axis as the energy scale, then the positivity bounds, they restrict the allowed parameter space. And in general, you will have, starting from the EFT at high energies, you use the renormalization group equation and obtain some values of the parameters at low energies. The first thing that I want to, as a summary, point out is that if you derive these positivities at tree level, but then include loop level information in your effective field theory, it is known that those loop level corrections may break the tree level positivity bounds. What I wanted to point out in this talk is that the conditions under which in the effective field theory we can identify directions in this parameter space which are sort of generically enhanced because they always grow towards the IR. And it's very relevant to find such, to identify such corners, because those will be the parameters that you want to look at your experiments, because those will be expected to have grown towards the IR and therefore become more relevant to look at. So finally, as outlook, we want to consider including 3-point interactions. Also, it would be interesting to not take completely the T to 0 limit, but maybe consider some non-forward extensions of our results. And then, yeah, you can ask about higher loops and higher multiplicity as well. So thank you very much for your attention.